¿Se escucha?
Mm.
Sí, que está dando ahí, ya no sé, todo.
In the previous 2 units in this week, we talked about Boolean functions, and most of this discussion has been theoretical. Starting with this unit, we're going to talk about how we actually implement these Boolean functions using hardware. In particular, we're going to talk about a general technique called gate logic, which, loosely speaking, it's a technique for implementing Boolean functions using logic gates. Now, what is a logic gate? Well, a logic gate is a standalone chip, or a very simple chip, or an elementary chip, which is designed to deliver a well-defined functionality, something like NAND functionality, AND functionality, OR, and so on. What is a composite logic gate? A composite logic gate is one which is made up from elementary logic gate and other composite logic gates. Or simply, it's a more complex gate than the elementary ones. And in this course, we'll develop things like multiplexers and adders. And obviously, most of you don't know what these terms mean. Don't worry about it. You will get acquainted with them and actually build them in the next few weeks in the course. All right, so let us begin with the most fundamental logic gates that we use in this course, called NAND. Here's the definition of a NAND. This is actually the standard diagram that we use to describe a NAND gate. It has two inputs and a single output. Everything here is binary, so A, B, and out are either 0 and or 1. Here is a functional description of this gate. If both inputs are 1, we output 0. Under any other circumstance, we output 1. And here's also a truth table description of the same functional specification. Any one of these descriptions is fine. Taken together, what we have here is an abstraction of the NAND gate. We didn't say a word about how this thing is actually working. We just describe what kind of functionality we can expect it to deliver. Okay, moving forward, here are three classical gates that pop up in every digital design project. We have an AND gate, which outputs 1 when both its inputs are 1, and 0 circumstance we output 1.
¿Qué canción? ¿Esa? No entiendo, dime.
And here's also a truth table description of the same functional specification. Any one of these descriptions is fine. Taken together, what we have here is an abstraction of the NAND gate. We didn't say a word about how this thing is actually working. We just describe what kind of functionality we can expect it to deliver. Okay, moving forward, here are three classical gates that pop up in every digital design project. We have an AND gate, which outputs 1 when both its inputs are 1 and 0 elsewhere. We have an OR gate, which outputs 1 when either one of its inputs are 1 and 0 elsewhere. And we have a NOT gate that operates as a converter. And we can put these gates together to create more complex functionality, as we'll illustrate later on. In particular, we can use these gates to create composite ones. So, for example, here's a three-way AND, which is an extension, if you will, of the simple two-way AND. And one way to build it is to use this trick here. We can take the output of one AND and feed it into one of the inputs of another AND gate. And if we wire everything correctly, this gate is supposed to deliver the required functionality. What we see in the dashed line rectangle around the implementation is a documentation of the interface of this chip. So the user lives outside the dashed rectangle. So the user sees only the three inputs and the output, as you see in the left-hand side of the gate description. If you want to go in or to sort of open up the black box, you have to see what is documented and done inside the dashed rectangle. So with that, I would like to say a few words about the notion of interface and implementation. The gate interface is the gate abstraction. This is how the user thinks about what the gate is supposed to do. Interface answers the question, what? At the same time, if you want to understand how the chip is doing what it's doing, you have to go deeper and go into, well, I'm not sure that deeper is the right word, but you have to go to another level of detail in which you actually, the black box opens up and you see how the chip is actually constructed. Or you do it yourself, if your job is to be the person who is actually realizing this abstraction. Now, the interface of the gate is unique. There's only one way to describe the gate's functionality. Otherwise, if there's more than one way, either you're not describing it well, or you're confusing the user, because there should be only one unique way to describe what a gate is supposed to do. At the same time, there may be several different implementations that realize the same abstraction. And some implementations may be more elegant, they may use less energy, they may be less or more expensive, and so on. So one abstraction, many different implementations. This is very typical in computer science. Whenever you build a large system, you have this duality. All right, now moving along, so we talked about the gate interface and the gate implementation. Let's talk about something known as circuit implementations. If I want, I can realize these gates using hardwired circuits like this one. And there's a certain sort of graphical language here that describes what's going on. When we want to represent the fact that the gate outputs 1, we assume that a light bulb will be turned on, and when the gate delivers output 0, the light bulb will be off. So if we look at this implementation of an AND circuit, we see that because of the architecture of this circuit, the light bulb will be on only if the two relays, both relays, are latched. Under any other circumstance, the light bulb will go off. And that's exactly what I want to do when I represent the AND logic. What about OR logic? Well, once again, if I have to build a circuit implementation of OR, I can realize it using this particular architecture. And here, it takes only one latch to close the circuit and turn on the light bulb. And once again, this is consistent with the desired abstraction of an OR circuit. Moving along, here's a circuit implementation of a three-way AND. And you can easily, I think, convince yourself that it will deliver the required functionality. And yet, I want to remind you that earlier in this unit, we also presented this implementation of an AND gate, if you recall. So I'd like to say a few words about these two different approaches to designing hardware. And I want to start by saying that in this particular course, we don't deal with physical implementations. And therefore, this whole discussion of circuits, transistors, relays, and so on, all this stuff, and what you see in the top left corner of the screen here, this is electrical engineering. It's not computer science. And the people who build these gates using circuits and similar technologies, some of them are far more advanced and sophisticated. Well, these people are called electrical engineers. God bless their souls. We have enough problems in computer science to worry about, so we are not going to worry at all about physical implementations. And all the designs that we are going to use in our course are going to be similar to what we did here at the bottom right of the screen. We are going to take existing logic gates, beginning with NAND and beginning with NAND only, and we're going to piece them together in some clever ways in order to generate and produce the required functionality. So this has been a unit in which we gave you a first brief introduction of logic gates. And in the next unit, we're going to introduce to you a language, some sort of a programming language called HDL, or hardware description language, with which you can actually build logic gates like the ones you saw in this unit, and far more complex logic gates and chips down the road. In previous units, we talked about how Boolean functions can be realized using logic gates. And in this unit, we're going to talk about how we can actually build and implement the logic gates using a formalism called hardware description language, or HDL. Once you build a logic gate in HDL, you can actually simulate it, test it, and finally build it in hardware, as we now turn to describe. All right, so let's begin this journey from abstraction to implementation. The first thing that you have to do as a gate architect is demand a full and complete description of the desired gate's behavior. And in this case, what we need is some sort of a truth table. In the case of XOR, it's a very simple truth table. And the truth table, along with the gate diagram, gives you everything that you need in order to understand what this chip is supposed to do. And what we see here is also sometimes called the chips interface. And indeed, using this information, you can start writing an HDL file that will look something like this example here. So we start the HDL program or the HDL file with some documentation, free form. You can write whatever you want there, which describes what the gate is supposed to do. And then we specify the name of the chip, the names of the inputs of the chips, and the names of the chip's output. And all this information, by the way, the name of the chip and the names of its inputs and outputs is typically given to you. It's not something that you decide. It's something which is part of the chip's contract, if you will. So you simply write it up using the syntax, and then you write the magic word parts, which describes that here begins the segment of your program in which you're going to describe how this chip is actually designed. Now, when you use such a chip, such a XOR chip, what we've seen so far is called the gate interface. And notice that this is everything that I need in order to use XOR gate. However, if I have to build this gate, well, that's a different story. Now I have to open up the black box and actually design it. So when we use chips, we always wear two different hats. There's the hat of the programmer who uses the chip as a chip part, and for this all we need to know is the chip interface. And there is the other hat of the chip's builder, which is what we're going to do now. So moving along, let's discuss how we actually build this chip from scratch. All right, so actually we are not going to build it from scratch. We can, if we need to, we can build it from NAND gates only. However, let us assume that we've already built an AND gate, an OR gate, and a NOT gate. Well, if we built these gates, or if someone gave us these gates that we can freely use, here's what we can do. We can inspect the truth table and figure out from the truth table that the XOR functionality can be described as follows. I mean, look at the truth table. The gate outputs 1 in 2 cases only. If A and not B, or if B and not A. That is, if A is true and B is false, or if B is true and A is false. This sort of jumps out from the truth table. You can either see it on your own, or as Noam described in one of the previous units, you can synthesize this insight or this Boolean function from the table itself. So once you come up with this insight, the next thing that you do is you think about it for a little while, and you come up with a gate logic diagram that describes how we can build this Boolean function using basic logic gates that we already have to our disposal. Now, developing such diagrams is a matter of experience, and the only way to gain this expertise is to see many examples like this one. So let's take this example and explain it in detail. So the first thing that we can do is draw the boundary of the chip diagram, or the gate diagram. So we use this dashed outline for this purpose, and what remains outside the boundary is the user's view of this gate. In other words, the gate interface. All the user knows is that he or she has a gate that has 2 inputs, A and B, an output called out, and altogether somehow this chip, as if by magic, delivers the XOR functionality. So we draw this diagram and this interface, and now we can delve more into the inner architecture. So notice how the A signal is being copied and sent simultaneously into 2 different destinations. One of them is the AND gate, and the other one is, and we see that when you write HDL code, you are allowed to take any signal and distribute as many copies as you want. This wire. So to use a formal language, HDL has unlimited fan out. You can fan out any given signal to as many destinations. All right, moving along. Notice that we're using some off-the-shelf gates, AND, NOT, and OR. Now, whenever you use an off-the-shelf gate, you are bound to use the names of the gate's input and output as advertised, so to speak. In other words, when you take the gate off the shelf, the gate comes along with what can be called the gate signature or the gate's API. So we have no degrees of freedom here. We have to use the official names of the inputs and outputs of every one of our chip parts. Now, the next thing that we do is let's focus on the red connections that we see here. These are the connections that we draw in order to connect the different chip parts together. Now, the rule is that every one of these connections has to be named, and it's our responsibility to come up with a sensible name. So that's what we do. We can call this particular connection not A, which is a sensible name, I think, a self-descriptive name. We'll do the same thing with not B. We can call this one A and not B. We can call this one not B, not A and B, and that's it. We have named all the internal connections in our architecture, and we can actually now move on to describe this diagram in HDL. So now we can actually move on and implement this diagram using HDL. So we return to the HDL stub file that we had before, and I use the term stub file to describe a partial HDL implementation, so to speak, that actually describes only the chip's interface. And typically it comes with the statement implementation missing, or put your code here, and so on and so forth. So this is the contract that we actually have to implement. And now, indeed, we are going to focus on the implementation section of this file. And basically what we do is we begin to describe the gate diagram one chip part at a time. And for each one of the chip parts that we have, we write a single HDL statement that describes the chip along with all its connections. So we have two, we happen to have two NOT chip parts, so we describe them. The first NOT has in equals A. This is the input. You know, the in input of the chip receives the A signal, and output of the chip goes into NOT A. We do something similar with the other NOT chip. Then we describe the two N chips, and finally we describe the OR chip. Notice, by the way, that I use the words gate and chip interchangeably, and that's perfectly okay. A gate for me is simply a simple chip. All right, so this HDL diagram is nothing more than a textual description of the gate diagram. Did I say HDL diagram? I meant the HDL file is a textual description of the gate diagram that we see at the top of the slide. Now, I'd like to notice that once again we have interface, we have implementation, and also note that the interface of the chip is unique. You know, there's only one way to describe this chip, and this is typically given to us by whoever commissioned us to implement this chip. At the same time, the implementation is not unique, and the same interface can be implemented typically in many different ways. For example, in the case of XOR, we can implement the XOR chip using 3 logic gates only. So, and it doesn't really matter how exactly we do it. You can think about it on your own if you want. But in general, there may be different implementations, and some of them will be less expensive. They will contain less chip parts, less connections, consume less energy, and so on and so forth. So the interface is unique, and the implementation varies. Now, I'd like to use this opportunity to make some general observations about HDL. And for ease of reference, I have placed in front of you what we saw earlier in this unit, the gate diagram on the right-hand side, and its HDL description on the left. So what can we say about HDL? First of all, we see that there are certain issues in HDL which are very similar to what we normally do in other programming languages. We have to worry about good documentation of our HDL program, just like we do when we write a program in Java or Python. We have to come up with good descriptive names, both to the chips that we use and to the connections that we create within the architecture. So readability is terribly important. You know, we have to make sure that our HDL code is self-descriptive and readable. And in order to do it, we also use indentation, and make the code look real nice. So all these things are expected from you when you write your own HDL programs. In addition, there are certain things which are really unique to HDL. First of all, HDL is a functional or declarative language. There's no procedure going on. There's no program execution going on. It is nothing more than a static description of the gate diagram. At the same time, we assume that at some point this descriptive code will go into some interpreter. Will go into, in our case, into a hardware simulator that can actually take this description and start to pipe values from the bottom all the way to the end. So we assume that there is some agent that will turn this implementation into something that is actually working. But this procedural part is not part of the HDL code. It's external to the HDL code. So because HDL is a functional link to HDL, first of all, implementation of our HDL program, just like we do when we write a program in Java or Python, we have to come up with good descriptive names, both to the chips that we use and to the connections that we create within the architecture. So readability is terribly important. We have to make sure that our HDL code is self-descriptive and readable. And in order to do it, we also use indentation, and make the code look real nice. So all these things are expected from you when you write your own HDL programs. In addition, there are certain things which are really unique to HDL. First of all, HDL is a functional or declarative language. There's no procedure going on. There's no program execution going on. It is nothing more than a static description of the gate diagram. At the same time, we assume that at some point this descriptive code will go into some interpreter. Will go into, in our case, into a hardware simulator that can actually take this description and start to pipe values from the bottom all the way to the end. So we assume that there is some agent that will turn this implementation into something that is actually working. But this procedural part is not part of the HDL code. It's external to the HDL code. So because HDL is a functional language, we can actually write those HDL statements in any order that we wish. It doesn't matter if you begin to describe the NOT gate or the OR gate. It's completely up to you. But it is typically it's customary to begin to describe your diagram from left to right, and this also makes the code more readable. Also, note that each time we use an off-the-shelf gate, we commit ourselves to using the gate interface, that is, the names of the inputs and outputs that come along with the gate documentation. Now, in the Hack computer that we're going to build in this course, we decided as a matter of convention to almost always use the letters A and B for a 2-input chip and out for a single output chip. And therefore, we are going to have many chip connections that look like A equals A and out equals out. Now, at the beginning, this formalism, these conventions will look a little bit strange. What is it? Inputs that come at it's completely use an off-the-shelf begin to describe your diagram from left to right, and this also makes the code more readable. Also, note that each time we use an off-the-shelf gate, we commit ourselves to using the gate interface, that is the names of the inputs and outputs that come along with the gate documentation. Now, in the Hack computer that we're going to build in this course, we decided as a matter of convention to almost always use the letters A and B for a two-input chip and out for a single output chip. And therefore, we are going to have many chip connections that look like A equals A and out equals out. Now, at the beginning, this formalism, these conventions will look a little bit strange. What does it mean A equals A, out equals out? If you think about it a little bit, and if you go back to consult these diagrams, you will see that these connections make a lot of sense, and actually they are very convenient from a programming perspective. You will realize that once you get your hands dirty and write some HDL code of your own. So I'd like to end with some comments about how the description languages in general. There are many of them out there, and yet the two most popular HDLs that at least I know of are VHDL and Verilog. These are the languages which are used, I think, in 90% of hardware design projects, but there are many other HDLs out there that can be used as well. Our own HDL is very similar in its spirit to the industrial strength HDLs that I mentioned earlier, VHDL and Verilog, and yet it is a very minimal and simple version of these HDLs, and for this reason, you can master it in something like 1 hour of reading a tutorial and beginning to write some HDL code of your own. And most importantly, our HDL, along with our hardware simulator, gives you everything that you need in order to build the computer described in this course, and actually any other computer that you may want to build using the knowledge that you will gain in the NAND to Tetris course. So if you want to read more about HDL, and you should, take a look at Appendix A in the textbook, and also read the HDL survival guide in our NAND to Tetris website. Both are actually available in the website. And you may want to also take the hardware simulator tutorial and learn how to actually read HDL descriptions and execute the underlying logic of these HDL using simulation. So this has been the unit in which we gave you a primer of HDL. And in the next unit, we'll describe, once again, how you can take your HDL designs and bring them to life within the context of the hardware simulator. In the previous unit, we learned how to implement a gate logic using HDL. However, nothing in what we did guarantees that the HDL code that we wrote is actually correct. We have no idea if this architecture that we put together delivers the intended results of the chip that we seek to design. So in this unit, we will close this gap, and we'll learn how we can take an HDL program and verify to the best of our ability that the program or the HDL file delivers the intended functionality of the underlying chip. Now, here's the big picture of what we're going to do. Given that we have a particular HDL file and we want to test it, we can load it into a special program called Hardware Simulator. We have written such program and made it available to you in our website. This program happens to be written in Java. And this program is designed to simulate and test HDL files. So we load it into this program. We interactively test all sorts of operations on this chip, and we call this mode of testing interactive simulation. Alternatively, we can write another file and using a special language that we designed, which we call the testing language, something that you can learn in a few minutes, we can put together a set of replicable tests that are predetermined. So we don't have to do things interactively. We can think ahead of how we can systematically test the underlying chip. We write it in what is called a test script, and then we load into the simulator two separate files. We load the HDL code, we load the test script, and then we send the simulator to work. The simulator goes through every step in the test script and subjects the HDL code to the specified tests in this supplied script. We call this mode of operation script-based simulation. And finally, if we want, we can record the output of the simulation on something called an output file, and we can even compare the results of the simulation to a desired output, which is stored in yet another file called compare file. So as you see, there are many new concepts and techniques involved in this practice of hardware simulation, and the purpose of this unit is to make all this new information concrete by walking you through a step-by-step process of testing a working example that will accompany us throughout this unit. Now, throughout this unit, we are going to present several software tools, actually just one software tool, the hardware simulator, and you are more than welcome to stop the video, invoke this hardware simulator on your own computer, and make sure that what we do can be done also on your machine. You can do all this if you have downloaded the software suite at the beginning of the course, and if so, the hardware simulator should be available on your computer, and everything that we do in the lecture can be done by you as well. So we encourage you to kick tires as much as you please. So let's go on and start with some concrete examples. So here's the example that I'm going to use throughout this unit. It's an HDL file describing the XOR chip that we talked about in the previous unit. So the code itself should be familiar to you, even though it's not terribly important for understanding this particular unit. All right, so once again, the fact that we wrote this very nice piece of code does not imply in any way that the code is actually correct. In fact, most likely it contains some errors, either syntax errors or logical errors or whatnot. So how do we test it? Well, here's what we can do. We can invoke the hardware simulator. The program starts running. We can load the HDL file into this simulator, and we can then enter zeros and ones into the A and B inputs and observe what is going on inside the chip. Now, how do we observe what is going on? Well, we have to tell the simulator to evaluate the chip's logic. The simulator will not do anything until we tell it to actually consider the new inputs that we entered and evaluate the chip's logic. And if we do this, the simulator will take these values, these zeros and ones or whatever we entered, and will kind of pipe them through the architecture. And at some point, something will come out from the output pin of the chip. So at that point, we can inspect what actually materialized. So we can observe the outputs of the chip, in this particular case, the value of the out pin. And if we want, we can also inspect the values of the internal pins like not B, not A, and so on. And the simulator gives us all these nice capabilities. In particular, here's an example or a screenshot of the hardware simulator in action. And the simulator contains or features several different panes. So let's talk about each one of these panes in isolation. First of all, at the bottom left of the screen, we see the HDL code that we have loaded into the simulator. This is a static view. We cannot manipulate or edit this code. If we want to edit anything, we have to use an external text editor, change the HDL code, and reload it. So this pane just gives us an idea of what is it exactly that we loaded into the simulator. Here, we can actually interact with the input pins of the simulator. We can click them and change the values. We have 4 different possibilities of zeros and ones in this particular example. This is a very simple chip. And once we do this, we can click this icon, which looks like a calculator. And once we click it, we basically tell the simulator to evaluate the chip's logic on the supplied inputs. At this point, the simulator will spin its wheels. It will take a fraction of a second, and something will come out. We can then evaluate the output of the chip. In this particular case, we have only one output called out. And once again, if we want, we can also inspect the current values of the internal pins. So altogether, this GUI gives us everything that we need in order to carry out sort of hands-on interactive simulation of XOR chip, or any other chip for this matter. All right, moving along, I would like now to give you actually a hands-on example of the hardware simulator in action. So let's do that and then go back to the lecture. This is the hardware simulator. And in order to use it, we have to, first of all, load an HDL program into the simulator. And we do it by clicking this icon here. So let us do it. And we see that we are in the NAND to Tetris folder. So within this folder, we're going to select projects. And within projects, we'll select project 0. And we see that we have a single HDL file here. So let us select it. This is the XOR file that we discussed before. And we loaded the chip into the simulator. Now, the pane at the bottom left right here gives me a display of the file that I just loaded. I can scroll back and forth. It's not separate. It's not terribly useful, but this pane is actually just a read-only display. There's no way to actually change the code when you are inside the simulator. If you want to change the code, you have to do it using an external text editor, and then you have to reload, of course, the file that you changed and saved elsewhere. So let us assume that we are happy with this file, and I want to actually simulate the chip logic. Well, I do this by, first of all, looking at the current input values, and we see that the default values of the A and B inputs of the XOR chip happen to be 0. So if I want, I can go ahead and change one of them or both of them to some other values. So let us change A to 1, and let us change also B to 1. And notice that nothing yet happened. In order to see how the chip responds to these changes, I have to reevaluate the chip logic. And I do it by clicking this icon here, the calculator icon. So let us do it. And we see that once we click this icon, the output becomes 0. And indeed, XOR of 1 and 1 is 0. If we want to see some other possibilities, we can once again manipulate one of the input pins, click the calculator, and we see that the XOR now emits 1 instead of 0. Another thing that we can do is inspect the values of the internal pins, which gives us yet another level of scrutiny, in particular when we try to debug the chip and understand why it is misbehaving for some reason. So this has been a very brief description of the first thing that you do when you use the simulator. You load the chip, you play with the input pins, you inspect the outputs and the internal pins, and this is the ABC of chip debugging and testing. I wish to remind you in closing that if you want to change the chip logic, you have to edit the HDL file using some external text editor, save the new file, reload it into the simulator, and rerun the tests in order to test the new chip design. Now, interactive simulation is very nice indeed, but at some point it can become rather tedious, especially if you have lots of bugs in your design, and each time you have to go through the same set of tests and so on and so forth. So with that in mind, we are fortunate that we also have the notion of a test script available to us. So here, once again, is the tested chip. And by the way, I allow myself to use the words chip and gate interchangeably. For me, a gate is simply a simple chip. So this is the tested chip, and here's an example of a test script designed to test XOR gate. Now, let us go through the test script kind of line by line. The first command in the test script instructs the simulator to load the XOR HDL file into the program. So even this step is taken care of. We don't have to do it ourselves. The test script will load the program for us. By the way, this is terribly important if you do repetitive debugging, because how do you debug a gate? You use an external text editor, to change the gate, and then you click save, and you go back to the simulator. So it's important to remember to reload the new version of the edited chip. So that's why we added this command to the test script. Now, once the HDL is loaded into the simulator, the test script begins a process of subjecting the chip to 4 different tests. The semicolon represents the ending of one particular test, if you will. And so we set the input values of the chip to 0 and 0. We evaluate the chip logic and observe the results. And then we go through the next test and so on and so forth until we complete all the possible, all the input possibilities for this particular chip. So this is how we carry out script-based testing, and it has many benefits. And far and foremost is the fact that we don't have to do anything laboriously, using our own intuition, because everything is predetermined. We have a set of replicable tests, and we just use the same tests over and over whenever we debug the chip, which can be 2 weeks or 2 months from now. So it's good to know that we can always repeat the same set of tests. So altogether, we will try to always use a test script. And the good news is that you don't really have to worry about how to write test scripts, because we are going to supply to you all the test scripts that you need in order to test the chips that you are going to design in HDL. So you worry about the HDL, and we are going to worry about the testing of your work. Another thing that we can do is keep track of the outputs of the simulation. So in particular, we can augment our basic test scripts with something like the following commands. We can, at the beginning of the test, when we initialize things, we can instruct the simulator to create an output file, which in this example we happen to call xor.out. And as we go through the testing, at the end of each test, we tell the simulator to output to the output file a set of values which is determined in the preamble of the script. So as you see, the third line of the script says the output list is A, B, and out. And so whenever the simulator will see the directive output, it will write to the output file the current values of A, B, and out. And at the end of the simulation, we can simply inspect the result of the output file and convince ourselves that the chip has actually behaved according to expectations. In fact, in this particular example, if you will inspect the output file that emerged from the simulation, you will notice that it is completely identical to the truth table of XOR gate. So it looks like the gate is well behaving. So here's a snapshot of the hardware simulation in action using a test script. And once again, we have the HDL code as we did before at the bottom left. of the screen. But we now have something new. We have a test script which can be seen on the right pane, which is some sort of a multi-purpose GUI area which we use for different purposes. And after we load the script, we can instruct the simulator to actually execute the script, we do it by clicking this control, and the simulator goes to work, and at the end, if we want, we can inspect the resulting output file. And here is also a demo of the same thing with an actual hardware simulation session. We will now show how to use the hardware simulator in order to test an HDL program using a test script. So the first thing that we can do is load the HDL program into the simulator. So let us choose the same XOR HDL chip that we used before. And then instead of playing with the input pins interactively, we can use this icon here to open a test script. And we see that in the Project Zero folder, we have one test script called XOR.tst. So let us load it into the simulator environment. Once we do it, this pane in the interface shows us the contents of the currently loaded test script. And we see that it begins with a few comments, and then following that, we see the actual testing commands. And the first command, or the next command to be executed, is highlighted by a yellow bar. We can call it the cursor of the test script. Now, we see that each command ends either with a comma or with a semicolon. And when we click the play icon, the simulator is going to execute all the testing commands until the next semicolon is encountered. Now, the first 4 commands in this test script set up the simulation so to speak. And so let us execute them. So I click this icon here, and we see that the cursor moved to the next batch of commands. And this batch says set A to 0, set B to 0. These are the input pins of this particular chip, and then evaluate the chip logic and output the result into the output file. So let us execute this batch of commands, and we see that indeed the A and B inputs are now 0, and the out of the chip happens to be 0, which seems to be right, because as we know, XOR of 0 and 0 should be 0. So let us execute the next batch of test script commands. This batch sets A to 0 and B to 1, evaluates the chips, and outputs the result. And indeed, we see that XOR of 0 and 1 ended up being 1, which seems to be correct. So executing the next batch of commands sets A to 1 and B to 0, giving the result 1, which also seems to be correct. And then moving along, we execute the next and final batch of commands, which set both A and B to 1. And we see that the XOR responds by emitting the value 0, which once again seems to be correct. Now, the test script for XOR gate is relatively simple because basically it simply executes every possible input combination as stated by the chip truth table. In more complex chips, such an exhaustive testing is less feasible, and therefore the testing scripts will likely be more complex. Now, as we tested the script has also written the results of every test script batch into the output file. This is the result of saying output in the, I'm sorry, this is the result of the output command. Now, if you want to inspect the output file, we can do so by going to this control here and selecting output. So let's do that. And once we do it, we see that the output file indeed looks exactly like the truth table of XOR, and this gives us yet another indication that the chip has operated to specification. Before we go on with this step-by-step working example, I would like to stop for a minute or two and say some general things about the general concept of hardware simulators. So first of all, there are many of them. Some of them are free and open source, others are proprietary and very sophisticated and very expensive. And in this course, we use a simple hardware simulator, which at the same time gives you everything that you need in order to build the hack computer and any other computer that you want to build using the techniques described in the course. So the supplied hardware simulator, which you have on your computer now, is a tool that once again gives you everything you need. And if you want to learn how to use it, there are several places to consult with available documentation. If you go to the nantotetris.org website, you can find a full chapter. I think it's Appendix A, and actually Appendix A and Appendix B in our book describe how to use the hardware simulator, and these chapters are also available freely on the website. And another thing that you should do is go through the hardware simulator tutorial, which is a stack of interactive slides that explain how to use the simulator, as well as all the examples that you saw in this particular lecture. And we HDL. We looked at a particular HDL file, which records the logic of XOR. We have supplied the simulator with a test script designed to test this particular code, and we also looked at the resulting output file and convinced ourselves that the HDL file is actually correct. Now, this privilege of looking at an output file and saying, yeah, it works, is something which is rarely available in real-life testing. Why? Because the chips that we normally build are far more complex than XOR gate, and there is no way to look at an output file of, let's say, an ALU or a CPU chip or something like that and say, yeah, it works correctly. It's we have to do it in a far more systematic and planned way. So is there a way to do it? Well, you bet, and that's what we're going to do next. In particular, we can carry out the simulation with yet another tool, which is called a compare file. So here's an example of a compare file. It looks exactly like an output file, and in fact, in its previous incarnation, the compare file was an output file of a well-behaving XOR chip. So someone, and we'll talk about this someone momentarily, someone has written an XOR chip correctly, ran it through the simulator, generated an output file, renamed it compare file, and gave it to us, and said, now you go and build your chip and compare it to what I did. So basically, we can take the compare file and load it into the simulator, and then start to do the simulation as we did before. And now in each step of the simulation, whenever we output a set of selected pin values, the simulator will compare the output set of values to the respective line in the compare file. And if the two lines will not agree with each other, the simulator will throw a comparison error. So this gives us the ability to not only record the outputs of the chip, but also compare them to desired results. So you probably ask yourself, once again, how do we generate these compare files to begin with, right? Well, we could have left it as a mystery, but there's no need to leave anything unexplained. So here's how we do it. We do it using something called behavioral simulation. In particular, consider this XOR gate that we saw before, and let us assume once again that this implementation is correct. And we put it into the simulator along with the script, we run it, we generate results, and then we simply rename it to be XOR CMP, and it becomes the official compare file of this chip. So what is special about this slide? Didn't we say everything that we said here before? Well, we did, but there's one detail which is remarkably interesting in this notion of behavioral simulation. And the thing which is interesting is that the chip logic can be implemented in any way that the designer wishes. So we can write this chip logic in Java or some other high-level language. We can run the program. We can generate an output file, and then once again supply it as a compare file. So this technique of writing gate logic using or implementing gate logic using a high-level language gives you the ability to plan and test your hardware before you even write a single line of HDL code, which is quite a sophisticated way to do things. So we can do everything in high level, and only once the overall design of our machine works properly, we can begin to implement each chip at a time in HDL. All right, so this has been the notion of behavioral simulation, and I want to go on and talk about how we actually carry out hardware construction projects. So the cast of characters in any hardware construction project consists of several players, of which I would like to talk about two. First, we have the system architect. Now, the system architect is the person who is told, go build a chip that supports a certain function of a digital camera or something like that, or go build a chip that monitors a certain medical device. So the architect has the exact sort of user-level specifications of the chip, and And the other member in the team is a developer, or more than one developer or more than one architect, and together they have to design this chip. So how do they do it? Well, the system architect looks at the overall desired operation of the chip, and then he or she makes some decisions about how to break this overall behavior into a set of smaller chips, if you will, or sort of lower level chips. And then for each one of these chips, the architect creates a chip API, which consists of the name of the chip, the names of its input and output pins, a test script, and a compare file. All these things are prepared by the system architect, who may or may not have some people to help him or her in his work. And finally, given these resources, the developers can actually go out and build the chip. So the architecture can do behavioral simulation, they can do whatever they want in order to test that everything fits together nicely, and at some point, the developers actually build this thing using HDL. So once again, that's an example of a well-planned modular design, and yet another example of divide and conquer, taking something very complicated and breaking it into a set of more manageable, smaller modules, each of which can be created and tested in isolation. So for example, the Hack computer, I could have told you something like go build a computer, and actually that's what we do in this course, but we split this job into the construction of something like 30, 30 different chips that together comprise the Hack chipset. So we, Noam and I, the course instructors, we play the role of the system architects, and you guys are playing the roles of the actual hardware developers. All right, so the developer's view, your view of a particular chip, when we tell you to build a chip, here's what you get. You're going to get a stub file that contains the documentation of the chip that you have to build along with its interface. You're also going to get a test script that we have written for you. You're going to get a compare file, and then taken together, what you basically got is everything that you need in order to, number one, understand the interface, understand what the chip is supposed to do, the compare file, and we also tell you how we are going to test it. All right, so what do you do with all these resources? Well, what you have to do is write the missing implementation. The missing implementation is the HDL code that should actually drive this entire show. So that's exactly what we're going to do in Unit 1.7, but before we go on to this unit, we also have to say a few things about multi-bit buses, which is a gap that we still have to close in the general description of HDL programming.
In this unit, we'll deal with the question how to deal with a bunch of bits together. Really, this shouldn't really be a whole unit because it's almost trivial, but still, because there is a little bit of technical details attached to it, it's probably worthwhile to spend 5 or 6 minutes on this thing in a short unit. So the basic thing we want to point out is the following thing. When we design hardware, lots of time we need to manipulate a bunch of bits together. First of all, it's going to be convenient, conceptually convenient, to think about a bunch of bits that are manipulated together as one entity, and allowing ourselves to think about it in a slightly higher abstraction level, not of the single bits, but of a bunch of bits together as one entity. The second thing is that, of course, since we're going to describe our chips, our hardware, in hardware description language, of course, we will need some kind of support for that in the hardware description language. So a bunch of bits together that are manipulated together and have one meaning are sometimes called buses, coming from some Latin word meaning many or multiple, something like that. So here's an example of how we can think about that. So when we want to add two numbers, and we will build in the next week, we will build some kind of chips that adds two binary numbers. Each one of these binary numbers will have a bunch of bits, actually 16 bits in our implementation, but we want to think about them as numbers. So our chip that adds two numbers will be described as having two inputs, an A input, which is 16 bits, and a B input, which is 16 bits, and one output, which is the out, which also has 16 bits. So in reality, our chip has 32 wires feeding into it, and 16 wires going out of it, but still it's convenient to think about it as two numbers feeding in and one number feeding out. In this way, we can actually also think about these kind of numbers when we want to use them. So this is how the same chip will be described in HDL. I'm only giving the interface here, the API, and omitting all the internal structure, which is exactly what you learn next week. So we have simply defined our inputs as A and B, and we have in square brackets the number 16, which means that each one of these is 16 bits, very much like the syntax for arrays in programming languages. Now, once we have this kind of notation, we can think about these numbers and entities and manipulate them in higher level chips. So suppose we need to build a chip that now adds 3 numbers, each one of them 16 bits. Logically, we of course know how we can do that. We can just add 2 of them. Now, once we have this kind of notation, we can think about these numbers and entities and manipulate them in higher level chips. So suppose we need to build a chip that now adds 3 numbers, each one of them 16 bits. Logically, we of course know how we can do that. We can just add 2 of them and then add the third one to the sum. So how do we do that? So we get as our interface 3 inputs, first, second, and third, each one of them 16 bits. And we need to have an output, which is just out, also 16 bits. And we want to manipulate it at this level of abstraction, not looking at all the separate bits themselves. This is how we do that in HDL. We have 2 internal chips. One of them adds to 16 bits, adds 16 chips that we've just seen. And we add the first and the second inputs and plug the result into a temporary variable called temp, which is also 16 bits. And then we take this temporary variable and add it to the, or temporary wire, if you wish, or temporary bus, 16 wires, and add it to the third, getting our final output. And this is how we can just manipulate inside HDL the buses as entities. Now, of course, we should also be able to actually manipulate and get access to separate bits in a bus, because at the end of the day, a bus is just a bunch of bits together. So here's an example of, suppose we want to have a chip that gets as an input a bus of 4 bits in this case, and outputs a single bit, which is the AND of all the bits in the bus. How do we do that? To do that, we will need to access bit after bit, and it then simply adds them one after another. And this is how we do that. And notice the syntax, and that's the important thing. The syntax here, when we put an index aside the name of a pin of a bus, we just mean the specific bit that we're talking about. We're using the convention in RHDL that is common to most programming languages nowadays, that a 4-bit bus has bits number 0, 1, 2, and 3. So the indices go from 0 to the bus width minus 1. And this is how we do that. You're gonna, in the next project, in this project, you're gonna have a bunch of chips that actually that's what they do. They take a bunch of bits in the bus and just converge them and just mash them together into a single value, and we call this multi-way chips. So this, we call this kind of chip here, and for way takes 4 bits and adds them together. Here's another example showing how we can manipulate bits inside buses, and in the context of another thing we'll do commonly in this week's project, basically taking a bunch of operations and doing them in parallel to each one of the bits in a bunch of buses. So in this example, we have 2 input buses, and we simply want to do a bitwise AND of them. Take the first bit of A and B, AND it together, and that should produce the first bit of out. Similarly, doing the set for the second bit, and so on. So here's how we do that. We need to have 4 AND gates. Each one of that AND gates performs operation on one of the corresponding pairs of bits, and we access a bit one after another, simply listing the 0th bit, first bit, second bit, and putting the AND gate on these inputs and producing the correct output. Immediately notice that the 4 bits of the out that we just produced go out as a single bus, because that's how it was defined in the API. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a bus into sub-buses. So the first example here shows what happens if we want to compose a bus, a 16-bit bus, from 2 8-bit buses. So this example is sometimes that you bus, because that's how it was defined in the API. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a AND gate on these inputs and producing the correct output. Immediately notice that the 4 bits of the out that we just produced go out as a single bus, because that's how it was defined in the API. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a bus into sub-buses. So the first example here shows what happens if we want to compose a bus, a 16-bit bus, from 2 8-bit buses. So this example shows that we have in our input 2 8-bit buses. So there are a bunch of technical conveniences sometimes that you want to use when dealing with buses. For example, you may sometimes want to break a bus into sub-buses. So the first example here shows what happens if we want to compose a bus, a 16-bit bus, from 2 8-bit buses. So this example shows that we have in our input 2 8-bit buses called LSB, least significant byte, and MSB, most significant byte. And if we want to plug them together into an AND16 gate, we can just take the first 8 bits of the bus and plug the LSB into it, and the second 8-bit bits and plug the MSB into it. And notice the syntax for doing that. If we specify a subrange inside the square brackets in exactly this format with a dot notation, then we just get a bus being plugged into the correct sub-bus that we want to do it. We can do that on the input, and we can do that on the output, and we can break them in different ways. Now, different hardware description languages deal with all these issues and have different syntactic conventions. And of course, for our hardware description language, which you will need to work with in the project, you can find the exact specification on the website. I would like to say just a few words about some peculiarities, if you wish, on RHDL that you may find convenient to use. First of all, we do allow overlaps of sub-buses. So you can take, let's say, bits 0 to 5 and output them as one bus of 6 bits, and then again take bits, let's say, 3 to 7 and output them as another bus. So simply outputting the same bus in multiple ways that may be overlapping sub-buses. We allow that. Another convention that we have is internal buses are just their width is completely deduced by what you plugged into them. So you don't need to specify the width of an internal pin. It's just if it was connected to a bus, it just gets the correct width that it was connected to. And the third syntactic convention that I would like to mention is the fact that if you want to plug lots of zeros or lots of ones into a bus, you can do it together in one command by using true or false as constants. And both of these cases you get are multiplied. So if you plug true into some bus, each one of the bits gets a value 1, and similarly for false, where each one of the bits gets 0. So now we finished this very simple unit about handling a lot of bits together, and now we're ready to actually completely specify the project of this week.
So now that you're familiar with HDL and hardware simulation, we are ready to get our hands dirty and actually go and develop some chips. So in this unit, we're going to give you all the information that you need in order to design the chips that we have to build in Project One. Before we go on, let us remind ourselves what is the general spirit of this course. Well, the story that we're telling you is that God told us, here's a logic gate, NAND, now go and build a computer. And when we asked, how can we possibly do that, God said, one step at a time. And in particular, the hack computer that we're going to build in this course consists of something like 30 different chips, and we're going to build them one step at a time. And in the first project, we start with NAND, which is God-given, or given by us, or you can think about it as some sort of an axiom that you can assume. And using NAND, we want you to build the following gates: NOT, AND, OR, XOR, and so on and so forth. So that's what you have to do for Project One. And why these particular 15 gates? That's a good thing to ask. And the answer is twofold. First of all, every one of these gates is widely used in almost any construction of a digital device or some version of these gates. And the second answer, which is more practical, is that these gates comprise all the elementary logic gates which are needed in order to build our computer. So Project One lays out the foundation that we're going to use in subsequent projects, because in other projects we're going to use these chips in order to build more complex and more interesting functionality. So once again, here are the chips that we have to build, and I have separated them into 3 categories, just that we can discuss it in a more organized fashion. So we have some elementary logic gates, widely familiar, NOT, AND, OR, and so on. We have 16-bit variants of some of the logic gates, and we have some multi-way and also multi-way 16-bit variants of the previous gates. And in order to make this all these new concepts more familiar, I will focus on some gates in every one of these categories and say a few words about them. And this, once again, will give you everything that you need in order to build any one of the gates in Project One. So without further ado, let's start to talk about multiplexers and demultiplexers. So what is a multiplexer? A multiplexer is a gate that operates as follows. There are 2 inputs coming in, and we denote them A and B, and there's a cell input coming in, so-called, from the bottom. Of course, in reality, there's no bottom and left, but I'm talking about this gate diagram here. So 3 inputs come in, A, B, and cell. What does the multiplexer do? Well, if cell equals 0, the multiplexer outputs A. If cell equals 1, the multiplexer outputs B. That's it. That's the desired behavior of a multiplexer. And here is the truth table of the multiplexer. We have 3 inputs, so we have 8 different possibilities, and you can convince yourself that the truth table is consistent with what we described before. We can also provide an abbreviated truth table of the multiplexer operation. Once again, if cell is 0, the multiplexer outputs A, otherwise it outputs B. So a 2-way multiplexer enables us to select and output 1 out of 2 incoming inputs. And this is a fundamental operation that is being used over and over again, both in digital design projects as well as in communications networks. So here's an example of how Moore's logic comes to play in the context of building what is sometimes called a programmable gate. Now, what is a programmable gate? It's a gate that can behave in one of several different ways according to our will. So here's a simple programmable gate that can act either as an AND gate or as an OR gate. If the select bit is 0, the gate acts as AND. If the select bit is 1, the gate acts as OR. And here's the truth table of the gate, and you can convince yourself that it's consistent with what I said earlier. And here's how I can actually build it. I can use 2 gates, an AND and an OR, provided, of course, that I have developed them previously. And I can feed the A and B inputs simultaneously to both AND and OR. And we call this before fanning out. So the A input is fanned out into both AND and OR, and over again, both in digital design projects as well as gate. Now, what is a programmable gate? It's a gate whose logic comes to play as well as in communications networks. So here's an example of how Moore's logic comes to play in the context of building what is sometimes called a programmable gate. Now, what is a programmable gate? It's a gate that can behave in one of several different ways according to our will. So here's a simple programmable gate that can act either as an AND gate or as an OR gate. If the select bit is 0, the gate acts as AND. If the select bit is 1, the gate acts as OR. And here's the truth table of the gate, and you can convince yourself that it's consistent with what I said earlier. And here's how I can actually build it. I can use 2 gates, an AND and an OR, provided, of course, that I have developed them previously. And I can feed the A and B inputs simultaneously to both AND and OR. And we call this before fanning out. So the A input is fanned out into both AND and OR, and the same treatment is done with the B signal. And then I use a single multiplexer to decide, if I want to output the result of the AND or the result of the OR. So the user of this gate that sees only the only the interface of the gate gets exactly what he or she wanted, a programmable gate. Here's the HDL code that implements this particular architecture. And if you want, you can stop the video and inspect this code and make sure that it's consistent with the gate diagram. So here's an example of a MOOCs in the context of a digital design application. How do we build a multiplexer? Well, we get all this information from the system architect, and we also get a stub file. And what we have to do, of course, is to write the HDL code. And it turns out that we can build a multiplexer using 3 gates, AND, OR, and NOT, which we wire in a certain clever way, and the result is the desired MUX logic. So it's up to you to figure out how to do the wiring and actually implement the desired multiplexer. All right, moving along, let us talk about demultiplexer. A demultiplexer looks like the inverse of a multiplexer. It receives a single input, and based on the selection bit, it either channels the input to an A output or to a B output. Okay, so it's kind of a distributor of a value into one of several possible channels. In this example, we have it's a 2-way multiplexer, so it's a relatively simple example. All the other channels get 0. Okay, and so the demux is basically an inverse of a mux. Of a demux is an inverse of a mux, if you don't like my pronunciation. And once again, it distributes a single input into one of several possible output channels. Once again, just like we said about what we said about the multiplexer, demultiplexing is also something which is widely used in digital design projects as well as in communication networks. And we're going to get, or you are going to get the stub file, and you actually have to implement the logic in HDL. All right, I'd like to give you an example of how multiplexing, demultiplexing is also something which is widely used in digital design projects as well as in communication networks. And we're going to get, or you are going to get the stub file, and you actually have to implement the logic in HDL. All right, I'd like to give you an example of how multiplexing and demultiplexing can come to play in the context of communications networks. So here's a typical situation in building a network. And the situation is such that we may have several channels coming in, let's say channels of music or several movies that we want to send over a single communications line. So the single line that goes here in the middle of the slide can be 5,000 kilometers long, and it may be sort of an underwater line and or satellite line. And through this single line, I want to send multiple messages. How can I possibly do it? Well, if everything is digital, I can put a MUX in the sending end of our story, and I can feed the MUX an ongoing train of 01010101. This can be done using what is known as an oscillator. And because the MUX is going to get a repetitive train of 0101, it is going to output blue, red, blue, red, blue, red. In every cycle, the MUX will output 1 bit from one of the 2 inputs. At the receiving end of this story, once again I put a different oscillator, and therefore the demux is going to distribute the incoming inputs according to the demux logic. It will output blue, red, blue, red, blue, red, blue, red, and so on. So this logic here, the demux and the MUX logic taken together, enable me to braid or interleave several messages over a single communications line, which may be very expensive, and therefore it pays off to use it for multiple messages. And by the way, another attractive thing about this scheme here is that it can be completely asynchronous, right? They don't have to operate according to a master clock. Every one of these 2 operations, the encoding and the decoding operations, can be done separately. All right, so we talked about MUX and demux, which were by far to use it for multiple messages. And by the way, another attractive thing about this scheme here is that it can be completely asynchronous, right? They don't have to operate according to a master clock. Every one of these 2 operations, the encoding and the decoding operations, can be done separately. All right, so we talked about MUX and demux, which were by far the most complicated chips in the elementary logic gates that you have to build. And let's go on and talk about one example of out of the 4 16-bit chips that you have to build. So we'll talk about N16. And N16 looks as follows. We have 2 inputs coming in. Both of them are 16-bit buses, and we have a single 16-bit bus coming out. And basically what we have to implement is a 16-bit AND operation. So it looks like this, right? 1 and 0 should give us 1. I'm sorry, 0, 0 and 0 is 0, 1 and 1 finally gives us 1, and so on and so forth. We're going to get 1 if and only if both inputs are 1 in the respective index that we're looking at. Now there's something which is a little bit deceiving in this example here, because the calculation of the logic here is not sequential. Everything is being outputted, boom, in parallel. And this also gives you some tip on how to actually build it. Okay, this is a straightforward extension of elementary AND gates. You can read more if you want about how to handle buses of data in HDL. And basically, once you get this stub file, we can implement an AND gate using a set of two-way AND gates. All right, so this has been what I wanted to say about the 16-bit variants that you have to implement. And finally, I want to discuss one example of the multi-way variant. The buses of data in HDL. And basically, once you get this stub file, we can implement an AND gate using a set of two-way AND gates. All right, so this has been what I wanted to say about the 16-bit variants that you have to implement. And finally, now there's something which is a little bit deceiving in this example here, because the calculation of the logic here is not sequential. Everything is being outputted, boom, in parallel. And this also gives you some tip on how to actually build it. Okay, this is a straightforward extension of elementary AND gates. You can read more if you want about how to handle buses of data in HDL. And basically,
Ricardo, ¿ibas a comprar el PlayStation también este año? No tienen que mandar. ¿Estoy escuchando? ¿Ah?
once you get this stub file, we can implement an AND gate using a set of two-way AND gates. All right. So this has been what I wanted to say about the 16-bit variants that you have to implement. And finally, I want to discuss one example of the multi-way variant, which happens to be actually quite a straightforward notion. Here's an example of a MUX 4-way 16. It has 4 inputs coming in. Every one of them is a 16-bit bus. We have a 2-bit selection coming in, and that is because you need 2 bits in order to select 4 different possibilities. And we have a stub file, and we can build this thing using several MUX 16 gates, as well as perhaps some other gates as needed. So what do we have to do in project 1? Once again, we have to implement all these gates, starting with nothing more than NAND and previously designed gates. So once you build NOT, you're welcome to use it. Once you build NOT and AND, you're welcome to use any one of these 2 gates, and so on and so forth. So how do we actually do it? How do we actually build every one of these gates? Well, we're going to give you some building materials, and we're going to use XOR as an example. So you have the gate diagrams from the book or from the lecture. We're going to give you this HDL file, which is available to you, and you can open it up in a text editor. And we're also going to give you a test script and a compare file. And here's the contract that we want you to play with, or to play by the rules of this contract. When you run your XOR HDL, that is, once you take this XOR file and implement it and add your own HDL, when you run the resulting XOR HDL file on the supplied XOR test, the test that we provide, your output file should be the same as the supplied compare file. If this will happen, you have built the chip to our satisfaction. Once again, if your chip generates the expected behavior that we have specified, then you are done with this chip, and you can go on to develop the next one. So for every chip that you have to develop, we're going to give you stub file, test script, and a compare file. All right, so the resources of Project 1 are listed in the NAND to Tetris website. You can look at the different files if you want. And there's no need to download anything, because if you've downloaded the course software suite, then all the necessary files that you need for this project are available in your projects/01 directory, and you're welcome to start working with these files and build Project 1. If you need some additional resources, you can look at what we did in the first week, just to sort of get you warmed up for this project. There is the HDL survival guide, tutorial, and the Q&A forum. You can consult with any of these resources in order to gain some confidence and actually go out and build Project 1. In closing, I would like to say a few words about what we call the Hack Chipset API. When you build a particular gate diagram like this one, you're going to use all sorts of chip parts. In this case, 2 AND gates, a single OR gate, and 2 converters, or 2 NOT gates. And the question is, how are you supposed to know what are the names of the input and output files, the input and output pins of every one of the gates that you want to use? Well, the answer is that if the gates that you use are so-called off-the-shelf gates, or if they are part of the Hack Chipset API, we provide all the necessary information about how to use them. And in particular, there is a document on the NAND to Tetris website that gives resources in order to gain some confidence and actually go out and build Project 1. In closing, I would like to say a few words about what we call the Hack Chipset API. When you build a particular gate diagram like this one, you're going to use all sorts of chip parts. In this case, 2 AND gates, a single OR gate, and 2 converters, or 2 NOT gates. And the question is, how are you supposed to know what are the names of the input and output files, the input and output pins of every one of the gates that you want to use? Well, the answer is that if the gates that you use are so-called off-the-shelf gates, or if they are part of the HEC chipset API, we provide all the necessary information about how to use them. And in particular, there is a document on the NAND to Tetris website that gives you the API of all the chips in the HEC chipset. This document is actually part of the HDL survival guide. So whenever you're not sure, what are the names of the inputs and outputs pins of a particular chip part, please consult this document and you will know how to use them. Another thing that I'd like to say in closing, before we end this unit, is that you can always use what we call built-in chips. For example, suppose you implement some chip called foo, and you want to use a chip part called bar. How can you do it if you haven't written bar before? Sounds a little bit impossible, but in fact, it is possible. So once again, if you don't implement some chips that are part of the chip of the HEC chipset, you can still use them as chip parts. All you have to do, if we gave you the stub file of bar, you have to change the name of this file to something else. For example, instead of calling it chipname.hdl, you can rename it chipname.hdl1. Once you do this, when you load foo into the hardware simulator, the simulator will look for an HDL file that corresponds to the missing chip part, and if it will not find it, it will by default revert to using the built-in implementation of the missing chip. So this gives us tremendous flexibility because it means that in principle, we can build these chips in any order that we please, although we recommend that you build the chips in the given order that they are listed in Project One. So here are some general best practice advice for Project One and for subsequent projects as well. Once again, we recommend that you build the chips in the given order because they're specified from the simpler to the more complex. If you don't implement something, you can put it aside and, if you want, get back to it later. And you can, if you want, design some helper chips, chips that we haven't specified, which will act like private methods in high-level programming. However, this is really not necessary, and we advise that you don't do it. There's no need to invent any new chips. Just use the chips that we provided, and you should be fine in completing this project. And in general, just like we always do in computer science, strive to use as few parts as possible. Try to create an implementation which is elegant, readable, and well done. Now, I'd like to end this unit with a few notes about frequently asked problems and questions that a student raised when working on Project One. Well, first of all, you have to realize that when you create your HDL program, you have to use some external text editor like Notepad or whatever editor of your liking. You cannot create HDL code using our tools. In particular, you cannot write code inside the simulator. Once again, do it in an external editor, and once you save your HDL file, you can load it into our simulator. The next point that confused some students is that you cannot use a chip as a chip part in its own implementation. There's no recursion in HDL. All right, so all the chips that you use when implementing a new chip have to be some other chips that you've implemented before, or some built-in chips, which are always available as well. Now, when you run your HDL in a simulator, if everything works well, you will get a message at the bottom left of the simulation saying something like simulation completed successfully. If something goes wrong, and if there's a syntax problem with your HDL code or anything like that, you will get an error message printed in red. So once again, some students tended to miss these messages. So pay attention to the bottom left of the simulator when you simulate your chips. Now, in Unit 1.6, Noam explained the whole notion of multi-bit buses. And one thing that we'd like to add to this discussion is that these buses are indexed from right to left. So if A is a 16-bit bus, then A0 stands for the rightmost bit, sometimes called the least significant bit or the LSB, and A15 stands for the leftmost bit, also called the most significant bit or the MSB. So this is just a convention that you have to keep in mind when you in this discussion, is that these buses are indexed from right to left. So if A is a 16-bit bus, then A0 stands for the rightmost bit, sometimes called the least significant bit or the LSB, and A15 stands for the leftmost bit, also called the most significant bit or the MSB. So this is just a convention that you have to keep in mind when you index your multi-bit buses. And finally, we want to emphasize once again that we provide all sorts of resources with which you can consult when you write HDL code. In particular, the book has a whole appendix dedicated to HDL programming, and this appendix is also available online in the NAND to Tetris website. And there's an excellent document called HDL Survival Guide, which was written by Mark Armbrust, and this is the first place that you have to go to when you get stuck with something and you need some advice. So this has been the end of our unit about Project One overview, and we are ready to go on to the last unit of this week, in which we're going to say to talk about some general observations about elementary logic gates. During the first week of this course, we built a suite of 15 elementary logic gates. And in the next week of the course, we're going to take this basic functionality and use it in order to build some more interesting and powerful chips like adders and arithmetic logic unit. Now, whenever we teach this course, every week of instruction, there's a whole set of issues and questions that come up about different aspects of building hardware and software systems. So we've decided to devote the last unit of each week to answer such questions. And we are calling this this last unit every week, a perspective unit. So here are the questions that typically come up at the end of this unit in which we deal with elementary logic gates. So the first question of the day is it possible to build a computer starting with a logic gate other than NAND? Well, I'll take this question. And the answer is indeed yes, it's possible. For example, you can use another elementary gate called NOR, which stands for not or, and base your entire computer on this atomic building block. Likewise, it is quite natural to start with a suite consisting of AND, OR, and NOT gates and use them to build the system. And there are a number of other possibilities. And in fact, it's quite similar to the way geometry can be founded on different sets of axioms. And each one of them can be yet another point of departure to build, all the power and theorems of geometry. This is not such a bad analogy. However, it turns out that NAND gates are very popular in physical implementations of hardware systems because there are many integrated circuit technologies in which it is quite cheap or relatively cheap to build NAND gates. As you well know, during the course, during the first week, we treated these NAND gates as black box abstractions. So the next question, which is directly related to the first one, is, well, if you actually had to build a NAND gate, how would you go about it? Noam, maybe you can answer this question.
Okay, so in this course, we sort of made a point of not going into this question because we feel that is already physics or electronics rather than computer science. But still, let us see an example.
A NAND gate, how would you go about it? Noam, maybe you can answer this question.
Okay, so in this course, we sort of made a point of not going into this question because we feel that is already physics or electronics rather than computer science. But still, let us see an example. There are, of course, many different technologies to implement a NAND gate and any other gate, but let me show you the simplest example, if you wish, of such an implementation. So here's an NMOS implementation of a NAND gate. We have a plus voltage, which is going to be 1, our logical 1, and a minus voltage, which is our logical 0, and we're going to connect them as follows. A little resistor here, which is a weak connection, and then two nice transistors, NMOS transistors, which we connect this way. This is going to be our A input, and this is going to be our B input, and this is going to be our output. So these are the two transistors that we have. So how does this implementation work? The basic functionality of one of these NMOS transistors is that whenever the input gate gets high voltage, then it connects the two other terminals. If it gets a negative voltage inside, it disconnects the two terminals. So let's see what happens. If both A and B are 1, then we get a high voltage here, high voltage here. These two terminals are connected by this transistor. These two terminals are connected by this transistor. So we get a connection all the way from the output to negative. And since this is a weak connection and this is a strong connection, our output is going to be negative or 0, as we want in a NAND gate, because when a NAND gets 1 and 1 as inputs, it gets 0 as output. In any other case, one of these two inputs is going to be negative, which means a low voltage. The transistor connected to the low voltage input is going to disconnect the two terminals, in which case there is not going to be a connection from the minus sign to the output, and so this weak connection to the plus is the one that's going to rule, and we're going to get a plus output, which is exactly what we want in a NAND gate, which is true. So this is a NMOS implementation of a NAND gate. There are many other technologies. This one is not used so much anymore since the 70s or 80s. And the important thing in this course is we do not care about the technologies. We do not care neither about this implementation or any other implementation. We want to abstract it away inside of gates that get true and false and output true and false, and we don't care how exactly.
So welcome back from the world of resistors and transistors. And once again, this is a level of detail that we are not going to get into in this course. So here's the next question that we have, and it's about hardware description languages. And the question is, how does the HDL that we used in this course and in this week, how does it compare to real HDL languages that hardware engineers normally use? Well, first of all, our HDL is a very real language because you can use it to design computers and simulate computers, and that's what HDLs are all about. At the same time, obviously, industrial strength HDL languages like Verilog and VHDL are far more complex and powerful than our HDL. Typically, they have a syntax which is some mix of the HDL that we use and something that looks like the C programming language. And they feature all sorts of high-level programming constructs like for and while, which eliminate the need to write a lot of repetitive HDL code. So it's very nice to use these capabilities. And they also feature, like our language does, they feature the ability to model and simulate the notion of time and clocks, without which you wouldn't be able to build sequential logic. Logic that ends up with which you end up building things like memories and counters and so on. So these languages are very nice, and at the same time, they are quite complicated, and it would take you at least a month or so to master these languages in order to begin writing some code for this course. So as an alternative, Noam and I decided to design a very simple dialect or a very simple version of HDL and offer it to you. It has all the capabilities that we need in order to build the computer that we build in this course, and you can learn it in 1 hour. The next question, which is from Noam, is as follows. The chips that we built so far were quite simple. How does one go about designing complex chips containing hundreds of parts and connections?
Well, the truth is that there is no simple general way of designing complex circuits. It's really a complicated design challenge, and you need human ingenuity to do it well. Now, there are many techniques that you learn in digital circuit construction courses. For example, there are techniques called Carnot maps that allow you to optimize a gate with a small number of inputs. Sometimes you can use various tools. For example, there are so-called silicon compilers where you specify what the functionality that you want, and the silicon compiler already has inside it a lot of logic and a lot of algorithms that can optimize gates for you. But again, it is not perfect algorithms. These are all heuristics because the general problem, the so-called NP-complete, you cannot find a computer program that does it perfectly. The real answer is that after all these tools and all these techniques and so on, at the end of the day, you use the usual tools of computer science, modularity and abstraction. You break a complex problem into simpler parts, and the simpler parts are simpler to optimize and to construct. And at the end of the day, after you use all your tools, after you use all your techniques, you go back and use this modularity idea.
So these were the questions that we chose to focus on in this first perspective unit of week one. As you can see, this particular format of the perspective unit is open-ended. There are numerous questions that can come up. Once again, we don't want to deal with the level of transistors and resistors. This is something that belongs to electrical engineering. We want to focus on computer science. And when it comes to hardware technologies and so on, there are many questions that Noam and I cannot answer either. So we welcome any questions that can come up. You can post these questions on the course Q&A forum. And if there are other students who have some knowledge about these areas, you are perfectly welcome to go to the Q&A forum of the website of this course and answer these questions on your own.
In this unit, we'll deal with it's actually 16 bits in our and 16 kind of notation. We can think about these numbers and entities in 16 bits. 16 bits, add 16 chips that we've just seen, and we add the first 6. A bus is just a bunch of bits together. So here's an example. This is how we get this number in just. So in this example, we have 2 input buses, and we simply want to do a bitwise AND of them. Take the first bit of each A and B AND gates. Other simply go out as a single bus, because that's how it sometimes that you want to use when dealing with buses. For example, you may sometimes want to syntax to find the exact
Mm. Ya ponle eso también. Dame besos. Mm. Mm.
¿Quieres agüita naranja? ¿De verdad? Porque no me gusta naranja.
Mm. Ya. Bueno, Gigi.